This video will show you how to work a hard problem in the AC mesh equations tutorial in Circuit Tutor. So I'll just click on that. And now we're going to do mesh analysis. The mesh currents of the interior meshes have already been defined. We've basically assumed that the outer mesh current is our reference mesh, so that one is not shown. And let's start here. Since we do have we have one current source, we'll need a current constraint equation. And that's a very simple equation, so let's do that first. And we see that this current source is shared between two interior meshes. So we will need a difference of mesh currents will be given by the value of that source. And that will be I1 goes in the direction of I1s, minus I2, which goes in the direction opposite to I1s. And then the value there will be the value of I1s, which is simply 4 angle 75 degrees. That's our current constraint equation. And now let's do the SOT variable equations. We have a SOT voltage and a SOT current. Notice that in the AC tutorials, we did not deal with SOT powers. That will actually be a separate tutorial eventually because that's a much more complex subject than it is in DC circuits. So our SOT voltage V0 is across a capacitor here. So we have two currents going through that. So we're going to do a SOT branch voltage, and V0 will be equal to a difference in mesh currents times an impedance. And now that will be I4, which is the one entering the positive side of V0, minus I1, which is the current entering the negative side of V0. And that multiplies, of course, the impedance, which a capacitive impedance is always a negative imaginary number, so it's minus J2 ohms in this case. Now we also have a SOT branch current, so we'll select that from our menu. And that's the I0, which is the current going up through the inductor over here, as you see. So I0 is going to be simply one non-reference mesh current, namely I4. So put an I4 there. And it's a plus sign because I4 does in fact go in the direction of I0. They both go up. So therefore no negative sign is needed in this case. Now we need to write KVL equations for each mesh, or perhaps a super mesh in this case. So let's select KVL equations. And let's start with mesh 1. And you say, well, there's a problem here because we need the voltage drop across a current source. And remember that the voltage of a current source isn't zero, because if it was, the current source would never be able to deliver any power and it would be absolutely useless. And it's also not the value of the current source, because that wouldn't have the right units to be a voltage value, right? The value of a current source is in amperes, not in volts. So that can't possibly be the right answer. So basically, we don't know what that voltage is, but what we're going to do is we're going to use this super mesh idea. So we're going to form, basically take these two meshes, I1 and I2, that are connected by this shared current source, and form them into a single larger path that we're going to go around the outside here, and that avoids going through the current source, so we don't need to know its voltage drop anymore, and that sort of finesses the whole problem. So first we're going to go through this negative J2 ohms. There's two mesh currents going there, so we'll need a term like that. Then the just the 2 ohm rather, is a similar term, and that has to sum to 0 because there's only two elements in that super mesh path. So starting in the lower left, as I always do, let's go this way. And so we're going to have I1 minus I4, and using the tab key to make this easy. And we have negative J2, which is the impedance. And then the next term going through here is going to be I2 minus I5 times the 2 ohms, because the I2 has the passive sign convention with respect to a voltage drop, which is plus here and negative here. Okay, so now having done the super mesh for meshes 1 and 2, now we go to mesh 3. Mesh 2, of course, by itself we can't do because the same reason we couldn't do mesh 1, and we don't need to. So now in mesh 3 we just have two elements. One has two mesh currents and the other one has only one non-reference current. So we will need a term like that and a term like that, and they will sum to 0. And so the first term would be I3 minus I5, which is net current going up, times the impedance, again a capacitive impedance, negative J9 ohms. And then coming back down here, going in a clockwise direction, we just have I3 times the 1 ohm resistance. So that was our KVL equation for mesh 3. Now for mesh 4, we're going to have an inductor with 1 mesh current, and then a voltage source, or fixed voltage value, and then finally a capacitor with 2 mesh currents. So we'll need a term like that. All that's equal to 0. And so let's start at the lower left and go clockwise in the direction of the mesh current, which is what I normally recommend. And so we'll have I4 times the J4 inductive impedance, as always measured in ohms, as all impedances are. Then we have this next voltage drop, but actually we see this voltage source is actually causing a rise in a sense because we go from negative to plus. That's going from low to high. So therefore we need a minus sign in order to add its drop. So we put a minus sign there, and then the value of the source of V1S is 5 angle 0, so we can put 5 angle 0. Or we could make this 180 degrees and make this a plus sign. That would be the same thing, given that negative 1 is 1 angle 180 degrees in polar coordinates. Then finally we have, coming back around here, we have I4 minus I1, the net current to the left through that negative J2 impedance. And we put in the impedance itself, which is negative J2 ohms, capacitive impedance. And that's correct. And then finally we'll do mesh 5. And again, we have 3 elements there. 2 of them have shared mesh currents, and 1 doesn't. So we'll use those terms there. And now, starting lower left, we first go through the 3 ohms. So we'll have, that's I5 times the 3 ohms. I guess I could put that term first if we like. First. And then the next one would be the capacitor. So we could have I5 minus I3 times the negative J9 ohms. That's going down through the capacitor. So I5 has the passive sign convention. I3 has the active sign convention. And then finally going to the left through the 2 ohm, we have I5 minus I2 times the 2 ohms. And remember that the coefficients of the mesh current for which we're writing the equation, if we're doing it the way I've described, will always have plus signs. So the I5 terms are always positive signs, and all the other mesh currents will be negative signs. Okay, and that's all of the equations we need. We just click no more equations. And you can read the detailed description of that if you like, showing the color coding and everything, but I'll skip that now in the interest of time.